Hello and welcome to CB Astronomy. Today I'm going to be doing something a little bit different. The CB in the channel name has a bit of a double meaning. It's both my initials and it represents chemistry and biology. So today I'm going to branch into chemistry for the first time in the channel's history. So what I'm going to talk about is one of the first things you learn about once you do chemistry, and that's the periodic table. Now it's great because it holds a really big amount of information in a very condensed space. So I'm not going to go into the history of it because, well, frankly, I don't want to, because there were so many retractions and tables put forward through history, and the video will end up being like an hour long, which isn't practical for anyone because there'll be so much information and a lot of it won't be relevant. So I'm just going to stick to a few trends that were spotted in the periodic table and how to read it. So if I've edited this correctly, there should be a carbon atom sitting in the one of the corners. There. So so with the carbon atom you'll see a number 6, letter C, maybe the name of the element, and a number 12. So the 6 represents the atomic number. This represents the number of protons that are in the nucleus. The C is the symbol for the element. Each element has a different one. And the 12 is the atomic mass, and that's the approximate number of protons and neutrons in the atom, but this varies when you get into isotopes. So like carbon 12 is a really common one that we have, but there's also carbon 13 and 14. 14 is used in carbon dating, but isotopes are another story for a future video, and I'm not going to get into it because again I will talk for an hour. So the mass of the elements increase the further along the table you go, and this is because the more protons and neutrons you have in the nucleus, the heavier the element will be. Just in case you're not familiar with the structure of an atom, I'm sure you are if you're watching this video, but just in case it's been a while. So an atom will consist of a nucleus which has protons and neutrons, and then it'll have electrons orbiting it. The protons have a positive charge, neutrons have a neutral charge, and the electrons have a negative charge. So the table has different groups as well, so each column in it has a different name. The ones of interest are, so group 1 is the alkali metals, group 2 is the alkali earth metals, group 7 is the halogens, and group 8 is the noble gases. The block in the middle is called the transition metals. To the right of that is, that's left for you. To the right of that is the metalloids, and to the right of them are the non-metals. So, down the bottom you'll see the lanthanides and actinides as well. Lanthanides and actinides. Apologies. They are a bit weird. There's a few special things that make them separate from the table, and again, future video. I'm gonna have so many video ideas. So as I said, just going to talk about the trends that go on in the table, and two that I'm going to talk about today are ionization energy and the electronegativity values. So electronegativity is the relative attraction an atom in a molecule has for a shared pair of electrons in a covalent bond. Electronegativity is the relative attraction an atom in a molecule has for a shared pair of electrons in a covalent bond. Now, the reason I can get that off so fluidly is because my chemistry teacher in secondary school was not very nice, and anyone who didn't know the definition had to write it down numerous times, and ever since then, it's been 7 years since secondary school for me, and I still have the definition embedded in my head. And although it's a big wordy definition, because scientists like to use big words to sound clever, it's actually a pretty simple concept when you break into it. So to break into it, I need to tell you what a covalent bond is. So there's a couple of different types of reactions. Sometimes electrons can be just taken from atoms to make new molecules, like salt is made up of sodium and chlorine, and so sodium is in the alkaline metals and chlorine is a halogen. So you have 1 electron in the outer shell of sodium and 7 in the chlorine, and because of like they want to be in a more stable condition, so the sodium will completely give up its outer electron, chlorine, and then 2 of them will be bonded together that way. But with a covalent bond, the electron is shared. So just as an example, we'll take methane. So methane is made up of 1 carbon atom and 4 hydrogen atoms. The reason there's 4 is because carbon is in the 4th group across, which means it has 4 electrons in its outer shell, and hydrogen has 1. So because of the octet rule, it states that, I'm paraphrasing here because I've gone off script, but well, I know it's my own fault before you pointed out Gary. Hi Gary. Yeah, so the octet rule will state that molecules, the way molecules bind together will form a layer of 8 electrons in its outer shell, and I really hope I'm not wrong in this, and I don't want anybody to correct me, but if I am wrong I apologise, and I'll research and edit it out if I am. But oh my god, I'm such a mess. But yeah, so where was I? Yeah, so with the covalent bonds, the electrons are shared between, so in our example of methane, carbon's electrons will be shared, the hydrogen electrons will be shared with the carbon and do orbits around both, leaving it as a stable molecule. But the electronegativity values vary throughout the table, it's not constant. So let me just so the value will increase from left to right across the table. This is because there's more protons in the nucleus, meaning that there's a higher charge within the atom, meaning that like the heavier atom will pull more on the electron because it has a higher positive charge than its parent atom. It decreases as you go down the table because there's more shells of electrons, and it creates a bit of a screening effect. And because there's more shells in the atom, it means that there's a bigger distance between the outer shell and the nucleus, which means it's further away from its positive charge, meaning a weaker attraction. We'll move on to the ionization energy. So the ionization energy is the amount of energy required to completely remove the outermost electron from a gaseous atom. God, my English is horrible. So very similar to the electronegativity, it follows the same pattern, that it will increase from left to right, and generally increase. There are some certain circumstances where it drops, which I'll get into in a future video on electronic configuration. But it decreases as you look down the table as well. So the reason that it increases from left to right is because there's more electrons in the outer shell, which means that the atomic radius is decreased, and therefore they have a lower pull per electron because it's being shared between all of them, and it makes it easier to remove that electron then because there's less attraction on it. The reason it goes down again is with the outer shells. There's more electrons in the way of the outermost electron, so it makes it easier to pull off, and it's called electronic shielding, if I'm not mistaken. But also the outer shells mean that the atomic radius is increased, which is another thing that causes less attraction. So there's a few factors which contribute to the ionization energy values. Oh, I apologize because I'm a mess. But anyway, thank you very much for watching and bearing with me as I fumble through this video. As you can tell, I'm a bit off today for various reasons, mostly tired from work, but I will be much better prepared for my next set of videos. And thank you very much for watching. Usual stuff will be in the description, the Instagram, Twitter and Snapchat. Add and follow them if you'd like to get updates on content, and if you want to see posts from me while I'm making and editing the videos. And of course I'll probably be drinking coffee in a lot of them, because it's pretty much what fuels the channel, and I think I'm after having a tad too much today as it stands, but what can you do? Yeah, thanks, see you later.